In this next lecture, we'll be covering composite beams. So I have two beams. Basically, a composite beam is a composite beam that consists of two or more materials. In this case, you can see that I have a beam that's comprised of portion 1 and portion 2. These two materials could be different, and they could have different areas as well, A1 and A2. And the distance Y1 bar and Y2 bar are for the centroids of each of these pieces that you see here. You can see that we're measuring everything relative to the top coordinates, as you see, and there is a neutral axis somewhere here. We'll have to figure that out later, but there is a neutral axis that we will figure out. This is also using Bernoulli beam theory that says that the plane cross sections remain plane during deformation. So we know that. Therefore, the strains in a beam will have to fit the form that we've been discussing so far, where the strains are equal to some constant k times y, which is just the coordinates through the thickness of that beam. So remember, this is the cross section of the beam. I'm not showing you three dimensionality of the beam, but what you see there is really the cross section. So the stresses in the beam will have to fit the form, since stress equals the modulus of the material times epsilon. Then if I plug this in here, I should get the stress in material 1, the top material, and then the stress in material 2 will have to be the one here, because E2 times the strain gives you the stress in the bottom material. And so, yeah, so we'll have to figure this out. Here's another example where you have a situation where you have this modulus and area, this modulus and that area. Well, our goal is to use a transformation, and the goal is to take the bottom beam, part of the beam, cross section, and make it so that it has the same materials as the one above. It's a trick, a mathematical trick that allows us to be able to study the problem in a simple way. So again, you have a beam that comprises of two materials. You can transform the cross section of the bottom material to make it longer or shorter, depending upon what the modulus is. But the idea here is to transform it so that the whole thing has the same material E1. And the only difference now becomes that this has a larger area to account for the fact that these two things are different. So I will show you how we're going to deal with this right now. But we'll move forward here. We'll first apply force balance. Again, out of the plane of this page, there is no stress, a resultant stress. So the individual integrals of force, stress, axial stress for part 1 plus the axial resultant stress for part 2, that summation has to be 0. So what I'll do, I know stress is equal to E1 times Ky, where E1 is the modulus of the top material, in case of constants to be determined. I'll plug that in there, and I'll plug in that one in there. So I get this equation here, and I'll use material 1 as a reference, for which I'll transform any other sections that exist. So from the previous page, we have this. You can see here K can cancel out. And if I divide E2 divided by E1, I define that as N. Then you can see here, if I divide this whole thing by E1, I get E2 divided by E1, that's N. So I'm going to use E1 as my reference material. and I'll transform all the other materials relative to E1. Y is measured from the neutral axis. So this Y is measured from the neutral axis, this particular Y, and Y uppercase is measured from the top surface. So yeah, that's your neutral axis, and this Y is measured from the neutral axis. So looking at these different Y's, you have this big Y here, you have this Y bar that points you at to where the neutral axis is relative to the top surface, and then you have this coordinate system that starts at the neutral axis and has the letter Y. You can relate all of them. So for example, this Y here, which is this one here, has to be equal to this whole Y minus Y bar. That will give you this Y here. So it looks confusing because there's a lot of different Y's, but let me break it up again. So Y1 bar is the centroid to this part. Y2 bar is the centroid of this part. Y uppercase is measured from the top surface down. And then Y bar is measured from the top surface to the centroid of the whole cross section. And Y starts at that location where the neutral axis is. And so it has to be the small y, this small y, is equal to uppercase Y, which is this one here, minus Y bar, which is the location of the neutral axis of the whole thing. So I'm going to plug that in here and see what happens when I do it. When I do that, you can expand this whole thing. You find that this integral y dA plus n times integral y dA is that. Everything else can be moved to the right-hand side. It turns out that this integral here turns out to be the moment of inertia, not the moment of inertia, the centroid of part 1 times the area of A1 of that part 1. So that's easy. And then we find that the integral of y dA for area 2 will turn out to be the centroid of part 2 times area A2. And then you see these integrals here that are quite interesting. What you notice is that Y bar is the location of the neutral axis or the centroid of the whole part, but Y bar is constant. Y bar comes out of the integral, and the integral of A1 dA is A1. Same thing here, Y bar dA. That integral here, Y bar is constant. It comes out of the integral, but the integral of A2 with respect to dA is A2. So I've simplified some of these, and I can now plug in what I got of this equation. Then all this whole thing simplifies into the fact that I have the centroid of the whole cross section times A1, the area of this part, this material, plus n, which I had defined n as the ratio of the modulus. Y bar, again, that's the location neutral axis again, times A2, the cross-sectional area A2. That's equal to Y1 bar, which is the centroid of this piece, times A1, the area of that piece, plus n, which is the ratio of the modulus referenced to E1. Y2 bar is a centroid location of this piece relative to the top surface, and then the area A2 is that. So now I'm able to solve for Y bar, and when I solve for Y bar, I get this expression, and Y bar, by knowing the modulus of these two materials, by knowing the areas of these two materials, and knowing the centroid of these two materials, I'm able to calculate the location of the centroid of the whole cross section, which is where the neutral axis is. Y bar, which is that. So now I'm going to move on to discussing the composite beam. And so for the composite beam, I have the fact that the moments can also be added. So I want to determine what the moment is. The moment is equal to this amount, y times sigma x1 for the material 1, dA minus integral y sigma x2 dA. For material 1, I have E1 k times y as a stress. I plug it in there and I give this expression. For material 2, I have EKY right there, modulus 2 there. This whole thing equals a moment. What I can notice now is that K can be factored out. You can actually factor E1 out because E2 divided by E1 is N. When I do the whole thing, I get minus E1 times K times the modulus, the moment of inertia of part 1 plus N times the modulus, not the modulus, the moment of inertia for part 2. So again, I'll let you pause it here, but pretty much straightforward. N again is the ratio of E2 divided by E1. Show that here. And so now from the previous page I had gotten this, I can solve for K and I get this formula here. So now I know what K is. And if you know what K is, if you recall, stress was equal to E1 times K times Y. So plug in K there, you know what stress is in terms of this. So when you plug everything in, you get that the stress is equal to this, and this stress is equal to this. We're ready now to calculate stresses for each of these pieces that you see here. If you were to have more than 2 materials, you can use the same method. But now you're going to have to define for more than one material, material I will be the modulus of material I divided by the modulus 1. And then you'll find the centroid of the composite cross-section as this formula here, where Y1 is a cross-section, is a centroid location respect to the top surface of material 1. And then for the ith material, that'll be the center of the ith material respect to this cross-section. Area AI of that particular material, and Ni is this ratio. And then this will be just the addition of the different areas of that material, ith material, plus A1, which is this material here that I'm referencing. The moment of areas can be found using the parallel axis theorem for each of the i's that I have. That's a lot of work, but it's feasible. The moment is known, and the inertia of part 1 is known. So this is just plain addition of these things to get that stress. Well, one step into an example.